about 30 minutes, if all goes well, the Italian satellite SIRIO will be launched into orbit. Here to tell us about it is Bob Goss, NASA's manager for SIRIO, and the flight operations manager from Italy, Stefano Trumpy. Stefano, good to have you with us. I wonder if you'd give us some background on SIRIO.
Thank you for the question. SIRIO program is an effort sponsored by Italian government and carried on by CNR, the Italian National Research Council, which is aimed to experiment on super high frequency telecommunications. Since October '74, when the project entered in its final phase, all government agencies, NASA, and all industries worked very hard to implement this mission, and now the spacecraft is there on the launch pad, willing to be put in orbit for starting its operational life.
Good. Why do you call it SIRIO?
SIRIO, as you all know, is the brightest star of the Canis Major, or big dog.
The dog star,
yeah,
of course,
star.
right.
Okay.
Tell us about some of the experiments aboard SIRIO, if you will, Stefano.
Yes, the main experiment is an experiment of propagation with different meteorological conditions at the super high frequency band. That means 18 gigahertz for uplink connection and 12 gigahertz for downlink connection. And we want to study the influence of various meteorological conditions in order to introduce new frequencies for commercial telecommunications. Because the actual communication frequency now are too crowded for having more television and telephone commercial communications.
I wonder if you'd describe some of the component parts of this satellite. We have a model here on the table.
Yeah. We have here this nice model of SIRIO. SIRIO is bigger than that, is about 1 meter and 40 centimeters of diameter and 1 meter and 90 centimeters of height from the antenna tip to the apogee nozzle. And here you may see most of the very important parts of the spacecraft. One of the most important, of course, is the apogee motor that will put the spacecraft from the transfer orbit to the near synchronous orbit. Then you can see the antenna, VHF antenna whips, which will be receiving and transmitting commands and transmitting the telemetry, which will allow us to control the spacecraft during its flight. Then you can see the thrusters of the jets, of the auxiliary propulsion jet, that will allow us to have the better orbit, to reach the target orbit and to maintain the spacecraft in its position during its operational life. Also in the black spots here, you have the sensors that allow us to control and to determine the real position of the spacecraft and the position of the spin axis. And all these are the solar shells that will power the batteries and will give to the spacecraft the necessary power during its life. And also you can see the antenna, SHF, yeah, the spoon SHF antenna, which will allow us to make all the experiments we have to do.
Well, that's quite a satellite. How long have you been here at Goddard, you and your colleagues now?
In fact, a small group of us have been here from 2 years from now. We started in July '75, and we started studying the control of the flight dynamics aspect of the mission, ranging from celestial mechanics studies through software problems to implement this. And also a group of us, since 5 months, has been working here for be trained to control the spacecraft from the multi-satellite operation control center here at Goddard. And I think that this period has been very, very essential to us because it allowed us to build our own ground control system, which will be operating in Italy when NASA will hand over the spacecraft to Fucino, to the center of Telespazio, which will control the spacecraft during its operational life.
I see. Then you aren't using just NASA ground control equipment.
No, in effect, but by the fact, we are using also other stations.
Mm-hmm.
As you know, the spacecraft will be launched from Cape Kennedy in Florida, and then the first station will acquire telemetry of the spacecraft will be San Marco Station, which is an Italian station located in Kenya. And after that, half an hour after, NASA station will start to acquire the spacecraft, I mean Guam and Aurora. And then in odd apogees, we will have Rosman, Santiago, and Ascension. And when the spacecraft will be in its final target position, will be handed over to Fucino, near Rome, and will be controlled by that station.
Mm-hmm. You mentioned San Marco, Stefano. Is this an international project similar to San Marco?
But
Well, let me field that question.
Okay.
The conventional NASA cooperative programs, such as San Marco, this differs greatly. In those programs, NASA shares the cost of the mission and also strongly influences the design, development, and the operation of the satellite. This is different. For this mission, Italy is reimbursing us fully for the cost of the vehicle and the launch services. And I should add as a footnote that because of that, the satellite is completely designed, developed, and funded by Italy. There's a difference.
Very good. Where specifically was the satellite built, Stefano?
the satellite was built in Italy and was assembled in CIA, the company that has been assigned the task of assembling the spacecraft by CNR. And all the parts of the spacecraft are being built in Italy with a few exceptions.
See, all Italian contractors and subcontractors.
Yeah, CIA is a consortium of industries which has been set up for building SIRIO. And then many of the Italian companies which were involved in aerospace has been involved for building the various components, like Air Italia, CGA, FIA, Galileo, Montedera, Selenia, SNIA Viscosa, and this is just the list of the...
This is really an Italian satellite, isn't it? All the way.
All the way.
That's wonderful. Okay, I understand that SIRIO will be in geosynchronous orbit. I think you mentioned that before. When will this happen?
We will need 10 days, or from 10 to 14 days, to place the satellite in geosynchronous orbit after launch. Then we will have to check the spacecraft health and to start the SHF experiment. And then about 30 days after launch, the spacecraft will be handed over to Fucino. The control will be taken by Fucino.
Mm-hmm. Who did you work with most closely while you were here at Goddard for 2 years, Stefano?
It's a very difficult question to answer. I have worked with so many people that I can't mention all of them. And many people from NASA and also NASA contractors. And this one has been one of the most rewarding aspects of our being here, because I think that both SIRIO and NASA people enjoyed working together and profited something both of us because
I'm
of
sure.
the matching of our two different lifestyles.
Very good. I'm sure it was enjoyable and profitable for everyone concerned. Bob, let's talk about Delta for a bit. You're known as Mr. Delta in many circles. I wonder if you'd tell us about the Delta launch vehicle to be used on this mission.
Okay, I guess the easiest way for me to do this is to use my standard props, if you don't mind.
Fire away.
Regular Delta viewers might be getting a little tired of looking at them, but for the benefit of our viewers, I'll try to give a brief description of the launch vehicle and a little bit about the launch sequence. The model that you see here and the illustrations fairly accurately represent the Delta 2313, which will be used in tonight's launch, with one major exception. That is that what you see here, the model and the pictures, show 9 solid motors on the vehicle. In truth, the SIRIO booster will have only 3 solids. The reason for this is that the SIRIO satellite is a relatively lightweight spacecraft, and we don't have to use any more than 3 solids, and that really affects a considerable cost saving. So a little description of the vehicle itself then. The Delta 2313 is 35.4 meters tall, 2.4 meters in diameter, has a gross weight of approximately 133,000 kilograms at ignition. With the 3 strap-on solid caster 2 motors ignited, the average thrust at liftoff will be approximately 240,000 kilograms. The long tank door first stage, measuring 22.5 meters in length, is powered by a Rocketdyne main engine system that burns liquid propellant RP1, that's a highly refined kerosene, and liquid oxygen. The main engine has a rated thrust of 93,000 kilograms at sea level and has a burn time of approximately 228 seconds. The strap-on solid propellant motors for this mission are 6 meters long, 0.8 meters in diameter, and weigh approximately 4,300 kilograms each. Each motor delivers an average of 24,500 kilograms of thrust to augment the first stage engine. The second stage, which is approximately 6.4 meters long, is powered by a TRW liquid propellant engine using nitrogen tetroxide and Aerozine 50 as the oxidizer and fuel respectively. The second stage produces a rated thrust of 4,400 kilograms and is capable of multiple restarts. The second stage also houses the Delta Inertial Guidance System, which provides guidance, control, and sequencing of the flight from liftoff through third stage separation. The spin-stabilized third stage is a thiacol solid propellant motor about 1 meter in diameter with a rated thrust of 4,300 kilograms and a burn time of 44 seconds. It is mounted in a spin table on the second stage. Prior to third stage separation, small rockets are fired on the spin table, which spin the third stage spacecraft assembly up to 90 revolutions per minute, which provides stability during third stage burn. The spacecraft is secured to the third stage motor by means of a specially designed attach fitting, which also affects separation of the spacecraft from the launch vehicle. The fairing or heat shield is a 2-piece shell 8 meters long, which protects the spacecraft from aerodynamic heating during the boost flight. To give the viewers a little better understanding, Bill, of the powered flight sequence, we have a short animated film which we will run now. At liftoff, the main engine and the 3 solid motors are ignited. The solid motors burn for 38 seconds. 70 seconds later, the 3 motor casings are jettisoned. At about 3 minutes and 50 seconds after liftoff, the main engine and vernier engines cut off. The vehicle has now reached an altitude of 90 kilometers and is traveling at a speed of more than 18,000 kilometers per hour. 2 seconds later, the staging sequence is initiated. Explosive bolts release the joint between the interstage and the second stage miniskirt. Compressed springs between the stages impart a separation velocity of about 1.4 meters per second. 5 seconds later, the second stage engine is ignited. Roll control is exercised by the second stage attitude control system, with pitch and yaw accomplished by engine gimbaling. At an altitude of about 125 kilometers, where payload protection is no longer required, the fairing is jettisoned. After burning 5 minutes, the vehicle reaches the programmed velocity and the second stage engine is cut off. The vehicle coasts for 13 minutes to an altitude of 217 kilometers. The vehicle is reoriented and the second stage burns again for 13 seconds. 1 minute later, spin rockets are fired on the spin table to impart a 90 RPM spin rate to the third stage to provide stability during the third stage burn. Once up to speed, the restraining pedals on the spin table are opened, releasing the third stage assembly. The spent second stage is then retroed. About 44 seconds after separation from the second stage, the third stage is ignited. After a burn of 44 seconds, the necessary velocity has been achieved. Following burnout, the third stage motor case is separated from the payload by means of an explosively actuated clamp band. Springs impart a small separation velocity. The spacecraft is now in the desired orbit. The short film that you just saw depicted the Delta flight phase, that is, the portion of the mission from the liftoff at Cape Canaveral to separation of the spacecraft at the equator. At this point, when the spacecraft separates, it's placed in an elliptical transfer orbit with a perigee, or lowest altitude above the Earth, of 231 kilometers, an apogee, or highest point above the Earth, of 37,700 kilometers, and an inclination, or tilt of the orbit plane relative to the equator, of 23 degrees. Now, after 4 revolutions in the transfer orbit, a command is sent from the ground which fires the spacecraft apogee motor. This firing imparts sufficient velocity and a change of inclination such that the spacecraft is then traveling in a circular orbit directly over the equator. Turning to the next chart, once again, here is the elliptical transfer orbit which I depicted and the final circular orbit. When the spacecraft's orbital velocity and altitude are finally adjusted by the spacecraft thrusters, the spacecraft orbital velocity exactly matches the Earth's rotational velocity. Therefore, as viewed from the Earth, the spacecraft appears to be fixed or stationary over a given point. This allows communications on a continuing basis from 2 points on the Earth via the satellite. And as we mentioned earlier, the SIRIO spacecraft will ultimately be positioned at 15 degrees west longitude. That's about it, Bill.
Very good, Bob. How many satellites have been successfully launched by Delta to this point?
Well, the record now for 132 launches since 1960 is all successes except 10. We've had 10 failures out of 132 launches.
So that's 122 successes. And this is going to be number 123, right?
123rd success, yes.
Very good. Okay, gentlemen, thank you very much for a very excellent briefing. Certainly appreciate it, and the best of luck with SIRIO.